In this video, we will discuss the derivative as a function. Our learning objectives are fairly straightforward. First of all, we have to understand what the derivative is so that we can apply it as a function rule. Apply the derivative as a command. If we are given the graph of a function f, we want to be able to figure out the graph of its derivative, f prime. Furthermore, we would like to be able to analyze derivatives based on either the graph or the function. The function would be the equation. And we'd also want to graph and interpret higher order derivatives. There are a lot of vocabulary introduced with this. You can see them all at the bottom, and we can progress from here. So first of all, what's the derivative? You'll remember we actually had two definitions. The derivative we could phrase as x, the limit as x approaches a, of f of x minus f of a over x minus a. This was one of the definitions we used. Although when we were working on problems, it was more common to use the one written in red, where we used the alternate form, f of x plus h minus f of x all over h, as that limit tends to 0. We're going to use the one in the red. You'll note it's the same piece that we had written there. This is our definition of derivative. It's the one that we will use more frequently. However, using the variable a is weird. I mean, think back to your previous classes. You've never had a spot where they're saying f of a equals a squared. They didn't really do things like that. It was far more common to use x as your input, x as the argument of your function. We will do the same thing. We're just replacing a with x just so it fits the format that you're more used to seeing. All right, so here's our first part. We are given the graph of a function f. We need to graph its derivative f prime. Please remember, what is the derivative? The derivative is the slope of a tangent line. So for a piece like this, there are a lot of them that we could look at and say, right here, our tangent line, and there we have a tangent line, and there we have a tangent line. Each of those tangent lines are horizontal, which means each of them has a slope of 0. At each of these x values, where we have this peak or valley, that's where the derivative is 0. Well, that tells us we have a point, and a point. Each of those are the peaks and valleys of our function, but they correspond to a horizontal tangent line slope of 0. Well, we could pick other ones and say, right here, what does that slope look like? Maybe a 1. So we could come up and at this x value, come straight up and get a slope of 1. Well, we could pick some other spots like right here. What does that slope look like? Probably -1. So we could come straight down and say there's a slope of -1. What about right here? What does that slope look like? A little bit steeper, especially right here. A little bit less. Well, by looking at these slopes, we can say this one looks like it's maybe -1.5. This slope over on the right looks like maybe 2. So we could say a slope of 2 for this x value. We'd have a slope of 2. Over here, we could say that's a slope of maybe -2. So we'd say -2. And by looking at the graph, we were able to figure out enough slopes that we could start plotting points, which would allow us to connect the dots into something about like this. Not perfect. We understand it's not a perfect part, but hang on. That one would have been there. I was looking at this from the side, and it came off a little bit weird. It was more like that. We understand it's not a perfect graph, but it's ballpark close, which is what we were trying to do with a quick sketch. All right, so example 2. f of x equals x cubed minus x. Find a formula for f prime. Well, we could start by saying we know our definition, limit h approaches 0, f of x plus h minus f of x all over h. The first thing we will need is to calculate f of x plus h. That will be x plus h cubed minus x plus h. Okay, so that would be x plus h, and then x plus h squared would be x squared plus 2xh plus h squared minus x minus h. And foiling that would give us x cubed plus 2x squared h plus xh squared plus hx squared plus 2xh squared plus h cubed minus x minus h. Okay, so if we took that piece, we could then have our numerator, x cubed plus 2x squared h plus, I want to simplify this more a little bit before we progress. Combining the like terms, x cubed, got it, x squared h, we have 2x squared h plus x squared h would be 3x squared h. xh squared plus 2xh squared is 3xh squared plus h cubed minus x minus h. Okay. When we start using that now, we have f of x, which I'm writing down now in blue, subtract f of x, so that would be subtract x cubed and plus x, all over h. And we've got that limit. All right, so what are some pieces that are going to cancel? Well, x cubed with x cubed will cancel. X with x will cancel, plus minus pairs. And then we could notice in the numerator, we have a common factor of h in all of it. So if we factor that out, we'd have 3x squared plus 3xh plus h squared minus 1 all over h. Canceling out the h's, we could then apply a direct substitution for h equals 0, which gives us 3x squared plus 0 minus 1, which gives us our derivative 3x squared minus 1. And there we go, we've got our answer. Definitely a lot of work, but we've got it. Our answer for A, f prime of x equals 3x squared minus 1. Now, to compare the graphs for part B, we got to have a graph, so let's take x and f, and we'll just say -2, -1, 0, 1, 2. We start plugging in some x values and just creating a table. -2 cubed is -8. -8 subtract a -2 would be +2, so we'd get -6. That gives us -2, -6 is a point. If we plugged in -1, we'd have 1 cubed, -1, subtract a -1. That winds up being 0. So we'd have here. Plugging in 0, we get 0. Plugging in 1, 1 cubed minus 1, we get 0. And plugging in 2, we'd get 6, which frankly should make sense. X cubed minus x is an odd function, so it has to have rotational symmetry. As a polynomial, it's also got to be continuous, so we wind up with a graph that looks about like this. Again, not a perfect one, but here's our graph of f. For f prime, we would have 3x squared minus 1, so we could have f prime as part of this, so negative 2 squared. Well, 3 times 4 is 12, minus 1 is 11. Plugging in negative 1 would be 3 minus 1 is 2. Plugging in 0 would get us negative 1. And because it's an even function, it has to have y-axis symmetry. We'd wind up with a graph that's about here. Well, when we compare the graphs, an important thing worth noting, and I'll put this in green. Right here, we have a horizontal tangent line. That's a slope of 0. You notice that it corresponds to where the derivative is crossing the x-axis. On the right-hand side, we have the same piece. Also corresponds to where the derivative is crossing the x-axis. This is how we could compare the graph of f and f prime. Pieces like that are the important characteristics, making sure that they match up with that quality, that they actually correspond with one another. Okay, similar issue now. If we have f of x equal the square root of x, we want to find its derivative f prime of x. Okay, so let's start by saying f of x plus h is equal to the square root of x plus h. F of x, of course, is just the square root of x. So when we take our derivative, that will be the limit of the difference quotient, f of x plus h minus f of x all over h. In order to continue this problem, I'd like to get myself a little bit more space so that we can work. Specifically, we know that if we try doing a direct substitution right now, we wind up with 0 over 0, which doesn't make any sense at all. And so we need an algebraic technique to simplify it. This is one that I would rationalize the numerator. Multiply by its conjugate. And when we multiply by the conjugate, I'm hoping it gives me something that will simplify nicely. It's a common technique that with these issues, with these problems, where you have roots involved. So we would have limit h approaches 0. Okay, so foiling the top, the whole reason we conjugate is to set up a difference of squares. That's x plus h, not plus. It's a difference of squares, not a sum of squares. So minus x over h root of x plus h, plus x. And now we could start simplifying. X minus x would cancel. That gives us just h over h, which cancels, leaving a 1 in the numerator. When we apply the direct substitution for this limit, we'd get 1 over square root of x plus 0 plus square root of x, which we could simplify root of x plus root of x. And our denominator, there are 2 of them. So there we go. We have found f prime of x. If our function is the square root, then its derivative is 1 over 2 times the square root of x. How are these domains related? Well, if we start looking at just the domain of f, and to create some room, I'm going to erase some of my work here. Well, all my work, I guess. If we wanted to look at the domain of function f, we know that there are three things that we have to look for. We need to have, or rather avoid, taking a logarithm of a non-positive. We need to avoid taking square roots of negatives. And we need to avoid dividing by 0. Those are the three problems that we can run into. Well, we have no logarithms, so no problem with number 1. Since these are square root functions, of course, worrying about the square root of a negative is going to be an issue. So for domain of f, we need x to be greater than or equal to 0. That way we can avoid the negatives. There's no division in that one, so we're okay there as well. But when we look at the domain of f prime, well, we still have the same square root of x. So we still need x to be greater than or equal to 0 for the square root to make sense. And just to further emphasize, that's the square root I'm talking about. But if we plug in x equals 0, yeah, the square root will make sense. But then we'd have 1 over 2 times 0, which is still 1 over 0, and that does not make sense. We cannot use x equals 0 because that's going to make us divide by 0. Well, to put these pieces together, those could combine to simply say x has got to be greater than or equal to 0. Please notice, the domains are not the same. With many functions, especially polynomials, the domain of a function and the domain of its derivative will be the same, but not always. In fact, it is incredibly common that when you take a derivative, you are going to lose domain values, and the domain of the derivative is going to be even smaller. Because keep in mind, derivative is slope. And we could have an issue where a slope becomes infinite. If you have slope being infinite, even if the function makes sense, the derivative won't. That's actually what happened in this particular problem. Now for example 4, we again need to calculate the derivative. So we have f of x plus h is part that we would need. Okay, so that's x plus h plus 2 over x plus h minus 1. Well, when we take f of x plus h minus f of x, we have this piece minus x plus 2 over x minus 1, which creates some fractions for us. In order to subtract the fractions, we are going to have a common denominator. So on the left, we are missing an x minus 1. And on the right, we're missing x plus h minus 1. Okay, now from here we will need to do some more foiling, some more expanding. All right, on the left we'd have, I'll do this one in yellow, x times x is x squared, x times h, x times 2, negative 1 times x, negative 1 times h, negative 1 times 2. Okay, we've got all those. And now we need to subtract on the right. So x times x, x times h, x times negative 1, 2 times x, 2 times h, 2 times negative 1. And so we wind up with all of that over x minus 1, x plus h minus 1. We can look at this and see that some pieces are now going to cancel. For example, x squared minus x squared, negative 2, positive 2. Positive x net with negative x. Positive 2x, negative 2x. And that is going to leave behind xh minus h minus xh. Oh, actually I have to take that part as well. I didn't see those, but those canceled. Minus xh plus xh. I didn't see those right away, so let's back this part up and get rid of even more. That leaves behind, okay, minus h minus 2h which we could start combining right now by noting that minus h, negative h minus 2h is actually negative 3h. So there's our numerator, here's our denominator, and that's our term, f of x plus h minus f of x. To continue this, we know that we would have to take it all over h, so this whole piece, over an h, which is of course h over 1, and we could multiply by 1 over h, multiply by 1 over h, which would cancel out the h's. All of that comes together to give us negative 3 over x minus h, x minus 1, x minus h plus h. Oh man, I'm getting my signs all messed up. There we go. This is f of x plus h minus f of x all over h. In order to finish it off with the derivative, we have to take the limit as h approaches 0. Taking direct substitution, if h is equal to 0, that gives us negative 3 over x minus 1 quantity squared. And so there we go. We have our derivative. Yeah, a lot of work, a lot of algebra. Need to simplify the difference quotient and then take a limit. Now please remember, functions are rules, and rules in math usually have some way of writing them. If I were to say take a square root, you know that there is a symbol that says square root. If we say take an inverse, you know that there is a symbol for inverses, and there are also symbols for multiplying. If we say multiply, you could use the dot, you could use the x, you could use parentheses for multiplication, but there are several different symbols that mean multiplication. Derivatives are the same thing, the same type. There are symbols that mean take a derivative. And unfortunately, there are a lot of them. There are a lot of ways to write take a derivative. Every one of these things means derivative. The most common one we've been using so far is f prime of x. Well, we've also described y equals f of x. So if you take derivative, it should match up derivative. That's also another way of saying the derivative of y with respect to x. It's another way of writing the derivative. Well, we could use y, we could use f, we could use this operator introduced by Leibniz, d dx. d dx is it's like a command. It says you take the derivative of this thing on the right hand side. It's also used for like derivative of f of x. Please note this is not the same thing as a subscript f of x. If we use the subscript, we would refer to the domain. Capital D next to a regular f is derivative. And it does get used this way for dx. That's the derivative with respect to x of the function f of x. I'm sorry to say that there are a lot of ways of writing derivative, and all of them get used. In part, it depends on the context of the problem. The most frequent ones that we will use are these four. That's not to say that we won't use the other ones, it's just these will be the most frequent ones we use. Continuing forward, we also have another vocabulary word that gets tied with this. If the derivative exists, we say that the function is differentiable. So in this case, differentiable and derivative are related to each other. They don't mean the exact same thing because the derivative is the actual slope function of our tangent line. Differentiable is the original function saying it's possible to take the derivative. All right, so here, where is the absolute value function differentiable? Where this is asking, if on the absolute value function, where does the derivative actually exist? Well, there are several ways that we can do this. We can do it with equations, and that's the form your textbook used. They actually go through and say, here's the algebraic equation for it. I would rather look at it and simply say, here is my, oh, that's crap, that is poorly drawn. Here's my absolute value function, which I'll trace out in blue. Where does the derivative exist? That's asking, where does a slope actually make sense? Remember, absolute value function is negative x if x is less than 0, and positive x if it's greater than or equal to 0. Well, if we're looking only on the left-hand side, what's the slope? Yeah, we can visually see that slope is -1. And if we now connect over to the right-hand side, what's the slope? We can visually see it's a +1 on the right-hand side. The only issue is, what about right here at the origin? What's the slope there? Because it looks like coming in on the left, it's a -1. It looks like it's coming in on the right to be a +1. How does that make sense? We've got this issue that when we're looking at it, we're trying to say, what's the slope? And we don't know if it's negative, we don't know if it's positive, and in fact we have a bigger issue because a tangent line only needs to glance off and keep going. We could actually have a tangent line right here. We could have the tangent line just be horizontal. We can have it be coming down here and just barely glance off and keep going. We can have a lot of different tangent lines that just barely glance at this peak of the absolute value and keep going. This is where we run into a problem, because when we want to say the derivative, we're saying the slope of the tangent line, one tangent line. But this is one where we don't have one tangent line, so this is a function that does not make sense. It's undefined if x equals 0. So where is the function derivative? Where is the absolute value function differentiable? It's differentiable where the derivative makes sense. It does not make sense at 0, so this is differentiable on all the real numbers except at x equals 0. This is a very important proof, or a very important theorem. We're actually not going to take the time to prove it, though. But the idea behind it is, let's suppose we have a function that is differentiable. If a function is differentiable, that means it is possible to take the derivative. If it's possible to take the derivative, that will guarantee us this is also a continuous function. Which, for the most part, you look at it and say, well, this isn't Like, how is this in any way helpful? You have to take the derivative and do all that work just to find out that it's also continuous. It's a lot easier to do continuous than it is differentiable. Well, think back to your logic sections of your geometry class that you would have taken. We could take the contrapositive of this statement. The contrapositive tells us if it's not continuous, that will also give us that it is not differentiable, which frankly should make a whole lot of sense. This should make sense because if we have a graph that's saying, oh, check it out, I've got this big hole and gap right here. I've got this big jump. How do you get the slope of a tangent line? It's like, hey, check it out. Well, it doesn't glance. You look at it and say, where is the tangent line? If you have this big jump, it doesn't make any sense. And we'd have the same problem even if we had a removable discontinuity where it was like this and we just said, oh, it didn't look up that well, so let me kind of redraw this and change the color so we can see it better. Even if we have a hole in the graph where we could try to draw a tangent line at that point where it just glances it, the tangent line is tangent to the graph at the point. That's saying this point must be on the tangent. Well, how could the point be on the tangent line when the point doesn't exist, when it's not on the graph? This is our problem. We can't take the derivative at a removable discontinuity, at a hole, for the simple problem that the tangent line doesn't make sense there because there's nothing there. This is a piece that is more helpful. If you can look at a graph and see that it is not continuous, that will tell us that it is not differentiable. Please be cautious though. You'll note over in the key points how we had this piece written out. A common mistake students will use is to try to say, I have a continuous function, and because it's continuous, I know it's differentiable. That is a very common mistake. It is not true. Our last example with absolute value actually shows that. Absolute value is a continuous function. When we look at this piece, it doesn't have a hole, it doesn't have a gap, it doesn't have a jump. We can draw the whole thing with just a single stroke of our pen. Absolute value is continuous, but we just showed it's not differentiable at the x value of 0. Be careful with that part. It's a very common mistake that students will make. More generally, we should have some ideas on what causes a derivative to not exist. Well, remember, the derivative is a limit. When we're taking a limit, if the limit does not exist, then the derivative does not exist. So what are some of the ways that the derivative fails to exist? Well, we've already seen one of them. If you have a jump discontinuity, and this is the graph of our function f. If f has a jump discontinuity, it's not differentiable. We just saw that if you have a removable discontinuity, and let me change the color so we can see it better. If we have a removable discontinuity, it's a problem. More generally, we can just say, put these two together and say, if it's discontinuous, removable discontinuity. Most of the time, these two things are put together in one graph, and they just say, if it's not continuous, it's a problem. I wanted to show you the two different pictures and say, if it's not continuous, I'll just bring this over and say, hey, there, now we have a problem. But there are other types. Well, we just saw another one. A sharp corner. Sharp corners are going to create some problems if you try to take the derivative, because we still have the same idea that on a sharp corner there's more than one tangent line. The last one is a little bit less intuitive. Remember, if we took the limit and the limit was infinite, we actually say the limit does not exist. The limit exists only for finite numbers. Well, that can happen if you have graphs that look like this. Approaching zero, you see how the slope of this line is becoming really, really, really close to vertical? In the limit, it actually does get up towards being a perfectly straight line, almost like a vertical asymptote. If you have infinite limits, or infinite slope for a vertical line, that becomes a problem. You'll sometimes see this kind of behavior closing in on something like this. These are the three things that could cause a derivative not to exist, so there are three problems that you have to be aware of and be careful for. We have seen that f prime is the derivative of f. But consider the idea. Is it possible to take the derivative of a derivative? That is, to get rate of change of a rate of change? Well, think of this. Can you take the square root of a square root? Yes. So we would be able to take the derivative of a derivative. Yeah, not a problem. As long as it makes sense, we can keep taking derivatives for as long as we want. We could take 1,000,000 derivatives. We could take infinitely many derivatives as long as they make sense. If we run into a spot where we have problems where it no longer makes sense, we have to stop. But it might keep going depending on what the function is. Now, here is a table that would prove fairly beneficial with understanding the interpretation of a function. The original function would be something like a position function. And we know they're not always going to be position functions, but for a lot of them, we have position function where something is located. The first derivative is the rate of change in the position. Well, if we were looking how fast is position changing, that is velocity. If we take the derivative of velocity, we are then asking, what is the rate of change in speed? Rate of change in speed is talking about how quickly are you speeding up or how quickly are you slowing down. That is acceleration. If we took the third function, or if we took the third derivative, we're asking, how quickly are you accelerating? Are you accelerating at a very, very quickly, so it slams on the brake? If you slam on the gas right away, or you slam on the brakes really quickly? Well, anybody who's ever slammed on the brakes quickly knows what winds up happening there. You get jerked. And that's what our third derivative is. It's worth noting that calling the third derivative jerk is not universal. It will not be listed in many textbooks. There are a lot of authors who don't give it a name at all. They just say it's the third derivative, and they describe it as rate of change in acceleration. But calling the first derivative velocity, the second derivative acceleration, they are always in books. They show up. Okay, so for the interpretation, I actually just said these pieces. That's the original function. And velocity is the rate of change in the position or in the location. Now, because I'm a little bit lazy, I'm going to abbreviate rate of change. Rate of change in the velocity. And jerk is the rate of change. Wow, that does not look like an R at all. Rate of change in acceleration. For our next example, we are asked, find and interpret the second derivative, f double prime, or f prime prime of x. I'm hoping that you recognize this is a function that we were working with earlier. We already did the first derivative here, and we obtained f prime of x equals 3x squared minus 1. So we will not have to repeat all of this work. We've already done it. So we can come back and say, come on, next one, next, come on. There we go. F prime of x was 3x squared minus 1. So we just need to finish it up and get f double prime of x, which means that we'll just have to do the derivative again, but we'll be using this new function for it. So let's start off with f of x plus h. This will equal x plus h, 3x plus h squared minus 1, which we could expand x squared plus 2xh plus h squared minus 1, which would then give us 3x squared minus 6xh plus 3h squared minus 1. Now if we took f of x plus h and subtracted f of x, that would give us subtract 3x squared, and subtract a negative 1 would be plus 1, which we could see would give us some pieces that cancel, which gives us just those two blue terms in the middle. Well, when we extend this further and say over h, this would be over h, you'll notice that we could factor out an h from the numerator, giving us negative 6x plus 3h over h, which would just cancel. And that's relevant for us because then we could say the limit as h approaches 0 of f of x plus h minus f of x all over h, which happens to be, actually this was f prime, f prime, f prime, 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 which tells us f double prime of x is the limit as h approaches 0, negative 6x plus 3h, which equals just negative 6x. Hang on. When I'm looking at this problem, I can see a mistake that I made. I actually accidentally changed the negative sign. You'll notice this was a plus 2x. So when I take 3 times 2, I should have gotten a positive 6. But down here, I wrote negative 6. I accidentally changed the sign. It was supposed to be a positive 6x, which would have given us a positive 6x, and this would be a positive 6. Our correct answer is 6x. Okay, so this is a piece that tells us the derivative, the second derivative. We still need to interpret it. So we can say the acceleration of f of x is given by f double prime of x equals 6x. Now, if we had a specific word problem, we could go into this even further, where we could talk about what is accelerating. If we wanted to know specific x values, like the acceleration at x equals 6, we could go further and explore deeper. But without having a word problem, it's missing a lot of the information that would grant us further insight with interpretation. Note this one. F of x equals x cubed minus x. Find the third derivative, f triple prime. Well, we've already said f prime of x was 3x squared minus 1. And we just did double prime. The second derivative was 6x. Now we need to take the third derivative, and it's the same process. F triple prime, F double prime, I didn't need 3, F double prime x plus h is 6x plus h, which is of course 6x plus 6h. So when we take f double prime x plus h minus f double prime of x, we get 6x plus 6h minus 6x, which just cancels, giving us 6h. Well, when we put that all over h, we get all over h, which you'll notice these pieces were already gone, which would allow us to cancel out the h's and get just a 6. Continuing by taking the limit as h approaches 0, and I'll fill it in for completeness. Evaluate the limit. Replace h with 0. There is no h. So it's just saying 6, 6, 6, 6, 6, 6, 6, 6, 6. We have the limit of 6. There is our triple prime. Okay, we found it. We need to interpret it. Notice that this is a constant number 6. No matter what x value there is, f of x has jerk of 6. Because it's a constant. It never changes. The jerk will always be 6. Doesn't matter beginning, end, it's just constant. So, find the fourth derivative. I'd like to point out, you don't keep going prime, 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 prime forever. We're not just going to keep adding more and more and more primes. Once you get to 4, the notation is to stop using the tick marks and just put the number for the derivative in parentheses. This is the fourth derivative. Well, this one's fairly quick. Third derivative was a constant 6. So to get the fourth derivative, that will be the limit as h approaches 0, f triple prime x plus h minus f triple prime of x over h, which is this limit, h approaches 0. And so replace every x with an x plus h. Here, there is no x. Because there is no x, we just have 6. And f of x is also 6. Well, 6 minus 6 is 0, so we have h approaches 0, 0 over h. And you may be tempted to simply say, well, I'm going to plug in h equals 0 and get the 0 over 0 case, which doesn't make any sense. But please remember, this is a limit. It's not saying h equals 0. But since h does not actually equal 0 itself, remember, in the limit, we're carrying out numbers like h is equal to 0.1, 0.01, 0.001, and their negative counterparts. Well, if you took 0 divided by 0.1, that's 0. If you had 0.01, it's 0. No matter what number you're plugging in for h, it's still not 0. And so every single one of these pieces are saying it's the limit as h approaches 0 of nothing but zeros, which actually is 0 then. So our fourth derivative, the rate of change in the third derivative, which is the jerk function, is 0, which is just another way of saying the jerk function is a constant. Well, that shouldn't be too much of a surprise. We just did that. We just did the jerk function and saw that it was a constant 6, so shouldn't be big news that the fourth derivative would be 0. All right, example 9. A manufacturer produces rolls of a foundation sealant from tar with a fixed width. The cost of producing X yards of the sealant is this fixed cost, C equals f of x. What is the meaning of f prime of x? Well, remember, derivative means rate of change. F prime is the rate of change in f. But f is actually the cost. So when we're talking about the rate of change in cost, we're saying how much more does it cost to do extra. Not just how much does it cost, that would be the cost function. This is the interpretation for our cost function. To address the cost per the cost, or to address the units for the function, the cost function, f is measured in dollars. If you're going to have the derivative of it, it's dollars per something. Every time you take the derivative, you're going to add another per. This is dollars per unit. So it's saying how much more extra dollars is it going to cost per 1 unit. So in practical terms, what does it say? What does it mean to say f prime of 50 equals 14? Well, remember, this is talking about the additional cost. Okay, it's going to cost additional money. The y value is what we are having for this part. That's our $14. But we still need to associate the x value with it. So we can put them in there. When you talk about the interpretation, you're pairing the specific x and y values together. There we go. Please note, this is not saying it costs $14 to make a total of 50 units. This is saying it costs $14 to make only the next one at 50. We don't know how much it costs to make unit number 49. We don't know how much it costs to make unit 50 or unit 51 or 47. All we know is that for the one additional unit, it will cost $14 to make that 50th one. So consider this. Which is going to be bigger? The additional cost of making the 50th unit, or the additional cost for making the 500th unit. In part, you have to think through the manufacturing process. If I were going to make, let's just say cars, because it's a good example. If I were building cars by hand, if I had to build one car, the cost of doing just one is going to be really, really high because I have to spend a lot of money to be able to build the machines that will allow me to make parts. Like I have to be able to make the tire. That's going to cost money. I have to have a machine to make tires. I'm going to have a machine that will make the floorboards. So it's going to cost me a lot of money to have a machine that will do that. Because frankly, are you going to grab a sheet of metal and hammer out the whole car by hand? There are a lot of costs right up front to make them. So making a small number means those costs are split amongst a small amount. Plus, if I'm making 50 of them, I may not know the exact, like the best strategies on how to do it quick, how to do it easy. But the more of them you do, you start getting good at it. You start finding the fast ways to do it. You find the efficient ways of doing it. And so what winds up happening is because you can do them faster, because you can do them easier, because you don't make as many mistakes that you have to fix, it will become cheaper to make the 500th one than it would be for the 50th. Just because you get better at doing it and you can have, you're better, you're faster, you don't make mistakes, it winds up being cheaper as a result. But there's going to become a point where you say, well, if I have to make 5,000 of them, if I have to make 5,000 cars myself, I don't think I could make 5,000 cars by myself, at least not in 1 year. Not even if they're model cars, I couldn't do 5,000 model cars in 1 year. And there's a big part about it. If I had a team, they could help me do that bigger number. But I don't know too many people are going to say, sure, let's make cars for free and not get paid for it. And it might be an issue that I have these machines that will make me my tires. I have these machines that can make me my floor plan. I have the machine that can make the hood. What if I need to buy more machines? What if the one machine isn't enough to do all 5,000? Well, if I have to buy more machines and I have to hire more workers to help me get it done, all of a sudden I have more costs. And so it's going to become more expensive to do the 5,000th just because I'm going to get more involved. I will have to start spending money on more things, on other things as well. Chances are, though, the 5,000th, without knowing the specific equations, it's probably going to be cheaper than the 50th, but maybe not. In large part, it depends on what the specific equation is, and we don't have a specific equation to really examine and see. Now, here is our last problem. We have this table, and it's going to give us the approximate values by providing the estimates from the national debt 1980 to 2005. Estimate and interpret the value of D prime 1990. Well, please keep in mind, this function is giving us D. It is not giving us D prime. D is telling us how much we owed, what was the debt in terms of dollars. D prime is dollars per year. It's the speed at which the debt was changing. It's not total debt. It's speed of change in debt. Well, for this particular thing, there are lots of different ways we can do it. I'm going to start off by looking at this piece and say, okay, here's 1980, here's 85, and then 90, and 95. 100 would be the year 2000. Then I have 2005. With my national debt, I'm going to come up here and say, all right, I need to put a proper scale on it, and they need to be evenly spaced. I just can't put the numbers down. My numbers go from 900 to about 8,000. So let's start off by saying this piece is 0. There's 1,000. and 2,000 and 3,000. And you'll notice how I'm trying to keep them evenly spaced. If we were using a calculator, we could actually create a scatter plot and get this more precise. But I don't want it to be calculator, calculator, calculator on everything. Being able to build a scatter plot by hand is something that can be beneficial. And so there's my 8,000. And maybe I would have wanted to have them a little bit closer spacing, but I'm trying to keep the spacing about the same. Well, we can start plotting the points and say 1980 had 930. And I'm going to use this in yellow. And 85 was 1945. 1990 was 32, 33. So about there. Then we had a little bit below 5,000. Then we had a little bit about 5,700. Then we had about 8,000. Okay. So if I'm trying to like connect the dots and say, okay, here's my function. Here's my function as a just rough guess. The derivative is slope of the tangent line. And so if we want to know the slope of the tangent line at 1990, we can come straight up to 1990 and say, here's a tangent line. What do you think that slope is? Well, if we're looking at slope, we could be saying rise over run. And so with this piece that I'm doing, it's very, very imprecise. I understand that. We're getting just a rough estimate. But what I could say right here, from 1989, which I could come over and say, as a guess, 3,100. I don't know what it would be, but I'm taking a guess at 3,100. And I can come over here at 1991, and come over from 1991, and that would give me 3,500, maybe 3,600. We're taking an estimate. We know it's not going to be perfect. And so this gives me my x values. It gives me my y values. I could calculate the slope, 3,600 minus 3,100 over 91 minus 89, which would give us 500 over 2, which is 250. And so there's our rough estimate answer. We have the derivative at 1990 was about 250. Interpret these results. This is a way of saying in 1990, please notice that's the x value. The national debt increased 250, but this is 250 in billions. And I'm pointing that out right here where I was reading. It's measured in billions of dollars. So we're saying $250 billion, which I'm hoping you notice is the y value. It's just a connection between the x value and the y value. So yeah, a lot of money. That's saying we spent $250 billion more in 1990 than we took in taxes. Overall, those pieces come together to look at our learning objectives. Understand that the function is a rule. It's a command that says, take the derivative. Based on the derivative, we were also looking and saying, what's the relationship between the graph of f and f prime? Remember, that was our very first problems where we were looking and saying, horizontal lines for tangents cause zeros on the x-axis in the graph. We also looked at analyzing graphs of functions, analyzing the derivatives so that we could say pieces like here at the very, very end, when we were saying some of the analyzing part was looking at the relationship between position, velocity, acceleration, and jerk, but also to do pieces like these, the additional cost for the next unit. The additional cost, where would you have more additional cost, and the rate of change in the national debt. Those are all problems that are looking like this learning objective. Oh, gotta go back. Those are analyzing derivatives. But we also looked at interpreting and graphing some of the higher order derivatives for the second, third derivative as well. With those 4 learning objectives met, you should be able to demonstrate your understanding.